Thank you everyone for coming back to this workshop after such a nice dinner at the Hoirige. And I'm Jun Nishimura from KK, and I would like to thank the organizers, in particular Harold, for setting up this nice workshop in such a beautiful city of Vienna. And today I would like to give a review of the status of IKKT matrix model as a nonperturbative formulation of superstring theory. And I also would like to present some new results, which I haven't shown before in any other workshops, namely the work done in collaboration with these people here, in particular Yuma Asano, who is in the audience, and also the other students of mine in KK. Okay, so let's get started. One of the main topics today is the IKKT model, as you can see from the program. And this model was proposed by these four Japanese gentlemen. Kawai and Tsuchiya are in the audience, as you know, and this was proposed almost 25 years ago. Okay? And this was proposed as a non-perturbative formulation of superstring theory. And this means that it is actually really a lattice gauge theory of everything, not only matter and force, but also space-time. And the action of this model is very simple. It's just given by this bosonic part and the fermionic part. And the dynamical variables are just n by n Hermitian matrices without any argument. So there's no space-time a priori in this model. It's just matrix model. And this model has SO9-1 Lorentz symmetry, under which A mu transform as Lorentz vector and psi alpha transform as Majorana-Weil spinor. And these Lorentz indices are contracted using the Lorentzian metric, this one, and therefore it has this symmetry. And this fact is going to play a very important role in my talk today. And this action can be also obtained, at least formally, by taking the zero volume limit of supersymmetric Yang-Mills theory in 10 dimensions. So if you know Eguchi-Kawai reduction, this is a kind of supersymmetric version of it. Okay. And then for a long time, the Euclidean version of this model has been studied. And the reason is that once you make a weak rotation, this model becomes well-defined. What I mean by that is that you replace this A0 in this action or in this model by I times A10, and now you regard A10 as a Hermitian matrix. And then the partition function is defined in this way, and integrating out the upsides, the fermionic matrices, you get Pfaffian. And here, the bosonic part is written in this way in terms of Hermitian matrices F mu nu squared. So this is positive definite, obviously. And in particular, this partition function was shown to be finite by these people a long time ago. However, there's an interesting feature here, namely the Pfaffian is actually complex valued. And also in this paper, it was shown that the fluctuation of this Pfaffian, the phase of the Pfaffian becomes milder if the lower dimensional configurations appear. Okay? If A mu here represent lower dimensional configuration, namely if only a few of them are non-zero and the others are zero, then the fluctuation of the phase of the Pfaffian becomes much milder. And this provides a possible mechanism for the SSB of the SO10 symmetry that this model has. And in fact, by doing some complex Lorentzian simulation of this Euclidean model, it was found that this SO10 symmetry is broken down spontaneously to SO3. So this implies the emergence of 3D space. And this was shown in this paper. But of course, there is no time in this model because we already rotated A0. It's just a pure space, three-dimensional space. So what can we do with it? Then we started to talk about the Lorentzian model. Without doing weak rotation, we thought that we should go back to the original proposal, namely starting from the Lorentzian symmetry. Okay? So in that case, so this paper started to discuss the Lorentzian model, as far as I understand. And the partition function was defined in this way, where we put I in front of the action. And this is motivated by the connection to the worldsheet action of type 2B string theory. Because in the original IKKT paper, this connection was discussed. And there, this IKKT action of the matrices are mapped to this action, which is actually the Schild gauge action of type 2B string theory. And in that case, this xi here includes also the time coordinate. So when you make a weak rotation, it's more natural to have I in front. And that's why we have I when we consider the Lorentzian model. So as opposed to the Euclidean case, where we don't have I here. So we are going to focus on this Lorentzian model. And in particular, I'm going to tell you that we need some regularization because as it stands, this model is ill-defined. And after the regularization, it has a surprising properties due to the non-compact symmetry of the Lorentz symmetry. That is the main message that I would like to convey to you. So the plan of my talk is the following. I will explain how to make the Lorentzian model well-defined, and then discuss surprising properties of this model, Lorentzian model, due to non-compact symmetry. That was very surprising to us, at least. And so I hope, I think you'll be also surprised too. And then I'm going to confirm these properties in the simplest case of n equals 2. N equals 2 means 2 by 2 matrices, and also omitting the Fermi matrices, namely just bosonic model. And we were able to do simulations and also 1/d expansion, which are both nonperturbative method. And we have agreement between these two approaches and confirm these surprising properties. So is there any questions so far? Okay, very good. So let me, yes. Yes. Okay. 2D is exceptional because if you consider only, let's say, A0 and A1 are non-zero and the rest is 0, then Paphian becomes 0. So 2D is special. So it only goes down to 3D. And that is consistent with our observation that happens really numerically. Yeah, thank you for a very nice question. And that point will be important later as well. Any other questions? Yes, please. Sorry? What is 3D? Yeah. Hmm? Okay, in this model. Yeah, okay, so this is just three-dimensional space. There's no time, yeah, because it's Euclidean. But when we consider Lorentzian model, we have time, so we can discuss whether it is 3 plus 1 or 2 plus 1. Yeah, yes, thank you. Okay, so, huh? Hmm? Mm-hmm. Mm-hmm. Yeah, yeah. Mm-hmm. I will explain that in a minute. We can prove that. Yeah. It can be easily seen, by the way, almost obvious. Okay. Any other questions? Okay. So let me explain why the Lorentz model is ill-defined as it is. And I'm going to regularize it later. Okay, so unlike the Euclidean model, the Lorentz model is not well-defined as it is. And well, let's look at this partition function. After integrating out the fermions, you get Paphian. But you see, this is just a pure phase factor. This SB is a real action for Hermitian A mu. Therefore, this is just a pure phase factor. And Paphian is just a polynomial in A. And it is actually real valued when A is Hermitian, unlike in the Euclidean case. But the point here is that if you take the absolute value of the integrand and just do the integration, obviously you get divergence. It's just that fact. That's what I mean by it's ill-defined. It's not absolutely convergent. But of course, you can make this convergent rather easily by introducing the convergence factor like this. So since we have this bosonic action, this term and this term, well, we have minus sign because of the Lorentz signature, but so this is not a positive definite as it stands. But then we can introduce these phase factors the opposite phase factors for the spatial directions and the temporal directions. And then as far as epsilon is positive and finite, this integral is absolutely convergent because of this. I think, well, this is the usual way to make the diverging integral a convergent one. And then we can take the epsilon going to zero limit and see whether it becomes finite or not. And by the way, this convergence factor, as far as epsilon is positive, the action is, this model is well defined. Therefore, we can also think of epsilon going to pi over 2. And that actually corresponds to the Euclidean model that I introduced already here. Okay? So the Lorentzian model is related or connected to the Euclidean model by just this epsilon. Epsilon 0 corresponds to the Lorentzian model. Epsilon pi over 2 corresponds to the Euclidean model. And the point here is that as far as epsilon is between this 0 and pi over 2, this model is well defined. So that means that these two models are actually equivalent. And you can also think of it as a kind of deformation of the contour, because this epsilon can be realized by just replacing a mu a0 and ai by a0 tilde and ai tilde with these phase factors. So the relationship between the two models is just given by this. So any correlators on this side can be calculated by using the Euclidean model. That is the message. Okay. And in fact, we can also confirm this numerically using complex standard method. And by the way, this equivalence has been pointed out to me for the first time by Yuma Asano in 2019. Okay, so the numerical confirmation is done here. As you see here, I plot this quantity and this quantity on the complex plane because these quantities become complex. You might wonder why it becomes complex, but it's actually, it can be understood because the Lorentzian model has a complex weights. This one is the weight when you calculate any observable. So even if the observable looks positive definite, because of the weight, which looks like this, well, in the Lorentzian model, you can get complex expectation values. And on the other hand, in the Euclidean model, you get real positive values because the weight, as you see here, it's positive definite weight. So Euclidean model gives positive quantities for these expectation values, and I plotted here the Euclidean results. But the Lorentzian result is complex, like this and this, and this is precisely given by this phase factor, as it should. Yes? This is the complex plane of this expectation value. This is the real part, and this is the imaginary part. And the Euclidean, yeah, this quantity in the Euclidean model is positive, real positive. So that's why I plotted here. But the Lorentzian model gives a complex value for this quantity, and therefore in the complex plane, it is given by this point. Okay. Yeah. I mean, of course, what you say is consider one. You could still have the Lorentzian model. Okay, so if you don't take the expectation value, then you can get just real space-time. That's what you're saying. Yeah. Okay, so thank you for the comment, but yeah, let's discuss that later. Anyway, if you would like to regard this expectation value as a space-time coordinate squared, then obviously they are complex valued, so the emergent space-time is complex, and moreover, since this and this will have a minus relative minus sign, well, essentially this means that the emergent space-time is Euclidean, as it should, because I have just said that this Lorentzian model, after doing this regularization, is just equivalent to the Euclidean model. So the question here is, how can we regularize the Lorentzian IKKT model in such a way that it becomes inequivalent to the Euclidean model? And in fact, there is a very simple answer to that, which we are not aware of for many years, but actually Harold was one of the person who pointed out to us. Namely, we can just add a mass term like this, okay? And then, well, adding just a mass term doesn't help because it appears here in the exponent with I in front. So when you take the absolute value, then it is still not absolutely convergent. But the very existence of this mass term allows us to introduce the convergence factors in a slightly different way than the one I just discussed. Namely, we can put these convergence factor in front of the mass term in this way. And then things will be changed. And moreover, this gamma here can be either positive and negative, and they can lead to different results, surprisingly. And what I can say is the following. When, I take this convention that trace A0 square appears here with positive sign and trace AI square with negative sign. And this is opposite to this IKKT action. Here we have minus sign for the temporal direction and plus for the spatial. So here I use this convention. But this is just a convention of the sign of gamma. Okay? Nothing, everything is general. Okay, and then the statement is that when gamma is negative, then it's more or less like this pattern, right? Because, so we can just make epsilon negative to make the integral finite. And moreover, since this and this is in the same direction, we can basically do the same contour deformation to arrive at the Euclidean version, namely with SOD, rotational symmetry. However, things will be totally different if you go to positive gamma, because in that case, you have to make epsilon positive as well. And then you are not allowed to make this contour deformation anymore, because if you do that, then you lead to an Euclidean model which has an unbounded action, which is kind of obvious because the sign of gamma is flipped. So if you have a well-defined Euclidean model on this side, you get an ill-defined potential, just unbounded action in this case. So in the positive gamma region, we expect that the Lorentzian model that you obtain in this way is inequivalent to the Euclidean model. And indeed, we will see surprising properties of this model for gamma positive. Okay? Yeah, that's right. So we take, right. So we take the epsilon going to 0 first, and then gamma to 0. That we have to do. But before taking gamma to 0 limit, we have to take the large N limit. That is the order of limits that we have in mind. But today I'm going to just discuss positive gamma without taking the limit and finite N. So taking the limits is a future program. Okay. So another thing that is nice with this mass term is that it allows us to study this model by classical equation motion. By that, I mean that if you rescale the matrices A mu in this way, then this term becomes just gamma squared times something that doesn't depend on gamma. And therefore, you can regard this gamma squared as a kind of 1 over h bar, the Planck constant. And that means that in the when gamma is large, that means h bar is small. Basically, classical solutions dominate this path integral. So going to large gamma, we can study the model by just solving the classical equation of motion, and then we can discuss which solution becomes dominant in the path integral as we decrease gamma to 0. That is a nice way of looking at this model. And then, you can think of this classical equation of motion. This one comes from the IKKT term, and this one comes from the mass term with gamma, the coefficient gamma. And we have actually solved this equation numerically in this paper and found a very nice result. Namely, yes, is it okay? First of all, let me remind you that A mu equals 0 is always a solution, obviously. And we call it a trivial saddle. But in fact, when we study this equation numerically, we find that typical Hermitian solutions show expanding behavior for positive gamma. So here, I don't discuss how we extract this time dependence of the scale of the spatial extent, but yeah, I hope you will understand what we are doing here after the next speaker's talk. So anyway, this is the time direction, and the spatial direction just have a minimum and expands exponentially. So this is obtained by just solving this equation. And this solution appears typically only for positive gamma. For negative gamma, we don't find any solutions like that. That was one of the interesting points. And the reason we didn't understand at that time, but now we understand it very well, as you see in the latter part of my talk. However, yes? Yes, that's right. Yes. Okay, and okay, so it's nice that we have this expanding behavior, but the problem here in the classical solutions is that, oh yes? Yes, exactly. Exactly. Yeah, so we, right, yeah, and Kostas is going to discuss more about how we extract that kind of information. Okay. Right, it breaks supersymmetry, that is right. Yes, we can think about that as well. But, well, as far as I see, in that case, it doesn't work like this. It's quite different from this gamma deformation, unfortunately. So yeah, let us discuss later maybe. Okay, let me just point out that as far as we look at the solutions, the number of space, dimensionality, is kind of arbitrary. You can obtain 2 expanding directions, or 3 or 4 or 5. Well, they all exist as classical solutions. So it is really important to include quantum effects. Namely, the effect of gamma being small in order to determine the space-time dimensionality. But anyway, the point I would like to make here is that, well, these solutions, these non-trivial solutions, has expanding behavior, and therefore it has a good chance to dominate the path integral because they have large entropy, for instance, compared to the trivial saddle point in this limit, n going to infinity and gamma going to 0 limit. So yeah, that's what we are hoping, and Kostas is going to show some numerical results related to this issue. Okay, and another thing I would like to mention here is the historical thing. Namely, this mass term was, well, discussed by many authors actually before us. In particular, Harold Steinacker's paper and his collaborators talked about solutions that they obtained after introducing this mass term. Okay, so now here comes the new thing. In fact, there are surprising properties due to non-compact symmetry of the Lorentz group. And you might think that rotational symmetry and Lorentz symmetry are more or less the same because it's just related to each other by weak rotation, but that is not the case. And let me give you some simple examples that shows this. Namely, if you consider just Gaussian integrals with rotational or Lorentz symmetry like this, well, this is not absolutely convergent, but you can make them convergent by introducing convergence factors, as I did before. And then you find in the limit of convergence factor going to 0, they are actually the same, basically. They are related to each other by just analytic continuation. So in that case, at least, well, Lorentzian or Euclidean doesn't really matter. They are the same. However, there are many examples that you think of where these two symmetries give totally different results. And this is the one simple example that I can show you. Namely, if you consider this k, this is another variable, and you integrate over k for the whole real axis. And then what you get is just actually a delta function. If you do the integration over k first, and then you just get the delta function of this thing, right? And that gives you just the volume of a sphere in this case, in this rotational symmetric case. But if you think of the Lorentz invariant case, after integrating out k, you get the volume of the hyperboloid of one sheet, which looks like this. And obviously, this is infinite. And you can also do an explicit calculation. You can, for instance, integrate out x first, and then by some residue analysis of k, you can easily convince yourself that this is actually true. Okay, so in this case, these two are not related to each other, obviously. And so in this case, yeah, these two integrals are related to each other by this weak rotation. But in this case, you cannot make any contour deformation to relate this one to this one. And that's why you get totally different results. Okay, so let's go back to our original model, Lorentz invariant IKKT model with a mass term. So the partition function looks like this, and we introduce this mass term with these convergent factors. And in the case of positive and negative gamma, we have this situation. But according to the discussions that I showed here, in the case of negative gamma, the partition function should be finite, because in that case, we can make a contour deformation to a rotation symmetric model. But on the other hand, when gamma is positive, this is not possible anymore, and therefore it is natural. It is possible that the partition function actually diverges, as we have seen here. That is, this is a possible scenario as well. And in fact, we will show that indeed the partition function is divergent for positive gamma in the simplest case of n equals 2 bosonic model. And I'm going to show it by numerical simulation and also 1 over the expansion. And they both agree. They both give the same results. That's what I would like to show. And the implication of this fact will be discussed in the summary. Okay, so can I continue? So I'd like to show some numerical results of n equals 2 bosonic model. But let me first say something about this model. So the classical equation motion looks like this. And in the case of this model, namely 2 by 2 matrices, we can exhaust all the solutions up to symmetry. That's quite a special thing for 2 by 2 matrices. For larger matrices, it's not possible as far as I understand. But in this case, we can do that, and we find that for negative gamma, the trivial solution is the only solution. And for the positive gamma, we have 2 more non-trivial solutions. And they are written in terms of Pauli matrices like this, and we call them Pauli solution and squash Pauli solutions for obvious reasons. And let me also talk about the symmetry, the remaining symmetry. But original model has SO91 times SU2, because we are working with 2 by 2 matrices. And for the trivial solution, this symmetry is not broken at all. But for the Pauli solutions, only the diagonal subgroup of SO3 cross SU2 remains unbroken. And in the case of squash Pauli, only SO2 cross U1. So this one is the less symmetric solution. But anyway, the point here is that non-trivial solutions like Pauli or squash Pauli exist only for positive gamma. Yes?
Could you also have
Doubled Pauli solution. Yeah, but this is not possible in the case of 2 by 2 matrices. This model is too simple to accommodate such more complicated solutions. So anyway, we have proven that these are the only solutions. No, I'm not saying that. Yeah, and these are just a symmetry of the solutions, and we don't know what happens in the gamma zero limit. Okay? Any other questions? Yes, okay. Yeah, this is fuzzy sphere. Yes. Yes, that is possible. Yeah, but we don't know that exhausts all the solutions. That is quite non-trivial. Yes, please. Uh-huh. You're talking about the convergence factor. I don't interested here. Yeah. Yeah. Okay. Yeah, using the Picard-Lasser theory is basically equivalent to introducing convergence factor. So yeah, you can do that as well. Thank you. Okay, so these are the solutions in this simple model. And yeah, so it is very nice that these non-trivial solutions exist only for positive gamma. And this is very important, as we will see. Okay, so what we have done with the numerical method is the following. So here we have the IKKT action with the mass term. And since we know that, well, we expect that this model is has this divergence of the partition function according to this argument, we introduce some regulator in the time direction to make simulation possible. And so we introduce this epsilon here only for the time direction, and that is sufficient to make the simulation work. And then we are going to make epsilon smaller and smaller and see whether divergence occurs. That's what we have done. And we have chosen a particular, well, the initial configuration to be the Pauli solution. This is our initial configuration, and let the simulation go with this. And then I'm going to show you some results obtained by the generalized Lexi symbol method. But here we sample only configurations only on the thimble associated with the Pauli solution. So in fact, in this model, we have 3 solutions, and therefore there are 3 thimbles that are associated with each of them. But in the simulation, we don't sum over all the thimbles. Just consider one thimble which is associated with the Pauli solution. And yeah, so that's how we did the simulation. Of course, we can try to sum up all the thimbles, but that is not what we would like to do here. Okay, and then we have calculated this quantity, trace A0 squared, and find that it is actually divergent as epsilon goes to 0. And it diverges like C over epsilon, where C is almost 15. And I'm going to show some analytic calculation of this power, this coefficient, which is 3D over 2 in the large D expansion, which is D 15 for D equals 10. So in fact, our numerical result is pretty much consistent with this 1 over D expansion. And we have also calculated this Lorentz invariant quantity, which turns out to be finite, even in the epsilon going to 0 limit. So this is a very nice result. And by this, we have confirmed the divergence of this partition function due to Lorentz symmetry. And let me show now the result. So here I plot this quantity. In fact, we take the real part only when we make this plot. And this x-axis is just 1 over epsilon, where epsilon is this convergence factor we introduced for the temporal direction. And we see a very nice 1 over epsilon diverging behavior as we go to smaller and smaller epsilon. And these data are for Pauli thimble, and these data are for squash Pauli. So, and they have different power. This is a typo, sorry. This should be 1 of, yeah. What I mean by that is 14.7 over epsilon for the Pauli and 0.46 over epsilon for the squash Pauli. I'm very sorry for this typo. But anyway, we have different coefficient for Pauli and squash Pauli. Okay? So that means that Pauli has faster diverging behavior than squash Pauli. And this has a very important consequence because this quantity that I plotted here in this figure is related to the partition function in this way, where epsilon is the convergence factor I introduced for the temporal direction. And therefore, this diverging behavior of this trace A0 squared implies immediately that the partition function should diverge like this. And the power C here depends on the solution. and it is 15 for Pauli and 5 for squash Pauli. So, yes? Yes?
You're saying that
Mm-hmm. Mm-hmm. Yeah, okay, so, yeah, I talk about only each saddle and each thimble, but still, I'm not focusing on just saddle point, but sample all the configurations along the thimble. Yes, yes. We have to know the saddle point to make this work. So that's what I mean here. Sample configurations only on the thimble associated with the Pauli solution. Yeah. Yeah, we can just sum them all. Yeah, this is a technical issue, but we know how to do it. Here in this study, we wanted to focus on one particular thimble. Yeah, well, thimble method, if you do it correctly or more cleverly, then you can sample all the thimbles, all the saddle points. But here, we do it in a rather simple way and try to focus on one particular thimble associated with this particular saddle. No, it doesn't run away. It is completely stable as far as we do this thimble method. Yeah. Yeah. So that's why we were able to obtain this result. But you see, these quantities diverge as epsilon becomes smaller and smaller. It becomes, let's say, 50 already. Epsilon is. Yeah, we haven't done that yet, but in principle we can. Yeah. Thank you. And the reason for this divergence is kind of understood intuitively by looking at this figure here. So even if the saddle, yeah, the Pauli solution corresponds to just 1, 0, 0, 0, 0 in this figure. And now you also have to sum over all the equivalent solutions that you can obtain by Lorentz transformation. And that forms this hyperboloid. And that is the reason why, if you look at just temporal direction, like trace A0 squared, that corresponds to looking at x0, you get divergent behavior. But if you just look at the Lorentz invariant quantities, like in this case, x mu squared, instead of just x0 squared, then you get something finite. So that's what is going on in these simulations, right? So, do you have any questions? Okay. So, so we have shown that the partition function diverges in this model for the Pauli and squash Pauli, and they have different diverging behavior. And since the Pauli solutions has larger power, negative power of epsilon, it diverges, well, faster. This implies that in the limit of epsilon going to 0, Pauli solution or Pauli thimble actually dominates the path integral in this model for positive gamma. And you might wonder that, well, since the partition function is infinite in the epsilon going to 0 limit, does this mean that the model is actually ill-defined? And the answer is no. In fact, if you look at just Lorentz invariant quantities, this quantity is finite, even in the epsilon going to 0 limit. So the divergence of the partition function is just due to the non-compactness of the Lorentz symmetry, and it's something like the gauge volume in ordinary continuum gauge theory. So, well, basically, Lorentz invariant quantities can be calculated without any problem, and they turn out to be finite. Yes. Okay, thank you. So let me quickly go through this 1 over the expansion. So what we do here is to expand A mu, this two, well, n by n Hermitian matrix is in terms of the SUN generators like this. So we have this number of components. And in fact, this combination of the variables becomes a kind of mean field in the large D limit. And we can show that in this way, in just 4 lines. So what we do here, we start from this partition function and introduce this auxiliary field H in this way. And if you integrate out this H, you go back to the original action. This is kind of Hubbard-Strauss transformation. And then you integrate out A from this, and then from here you get some log determinant K with some coefficient, which is D, because you have D matrices basically. And after rescaling this H in this way, you get an overall factor of D in front of the effective action. And here D, this number of bosonic matrices, appears as a parameter in the exponent like this. So if you consider largely D limit, then the path integral of H is dominated by the saddle point, which you can obtain by solving the saddle point equation. And in this case, the saddle point equation is nothing but this kind of equation. And that we can solve in the n equals 2 model as again, although n equals 3 case is not very easy, and we haven't done that yet. In the n equals 2 case, we can exhaust all the solutions, saddle point solutions to this equation. And again, for negative gamma, we only find this, but for positive gamma, we have 3. So you can naturally identify these 3 solutions to those classical solutions in the original matrix model. And by just looking at the symmetry that these solutions saddle point has, you can identify this as the trivial solution, this as the Pauli solution, and this as the squashed Pauli. Now, there's one subtle issue here in this 1 over D expansion, and that is the fact that you have actually a singularity along the original integration contour, which looks like this. And this is the point where this determinant K vanishes. Determinant K is the term in the action here that you obtain after integrating out A. Okay? And the reason why the singularity appears on the real axis is very easy to understand. It just simply reflects the fact that a model like this, which is not absolutely convergent, this is not well defined. Okay, and this fact is true also for the rotational invariant case where I replace A0 by I times AD, like this. So let's discuss this SOD, rotationally symmetric model first. In that case, we can introduce this convergence factor in the original matrix model, epsilon, and that will shift this singularity to the upper half plane. And therefore, this saddle point, this is the trivial saddle point. This is basically the saddle point that corresponds to Pauli solution. These become relevant saddle point because we can shift this singularity once you introduce this convergence factor. But if you look at negative gamma case, effectively this singularity is shifted in the opposite direction like this, and then this saddle point becomes irrelevant because singularity will prevent you to flow from real axis to this saddle point. So that is in fact consistent with the existence of the Pauli solution only for positive gamma. For negative gamma, Pauli solution doesn't exist, and this mean field approach reproduced this fact nicely. Now, then let's consider the Lorentzian case. In that case, we have this opposite convergent factors for temporal and spatial direction, and that's why the original singularity on the real axis will be split into 2. This corresponds to the temporal convergence factor, and this corresponds to the spatial one. Yes, spatial one. And because of this, you obtain a new saddle point between these 2 singularities. And if you and then you can calculate the partition function around these saddle points, this one and this one, very easily, and you get these results. So the phase factor here are the same, but the gamma dependence is different. They have, this one has positive power, but this one has negative power for gamma. And moreover, this one diverges as epsilon goes to 0. So the new saddle point we obtain in the Lorentzian case actually diverges in the epsilon 0 limit. Okay, so we have these 2 partition functions, and then we can see which one actually dominates, and we can easily find that there is actually a critical value of gamma, which is basically square root of epsilon, 1 over epsilon. And below this critical value, actually, let's see, new saddle point dominates, but above this critical value of gamma, this saddle point that was there from the beginning actually dominates. So there is a kind of Stokes phenomenon. So we can actually probe this transition by calculating these Lorentz invariant quantities, because this quantity can be obtained from the partition function in this way by taking the derivative with respect to gamma. And this is the prediction from this 1 over the expansion. And for the new saddle, we have this negative sign in the imaginary part of this quantity. So by looking at the imaginary part of this Lorentz invariant expectation value, we can see this transition. And that is precisely what happens when we do this numerically. So when gamma is small, we see the property of the new saddle. And when gamma becomes large, we have this original Pauli solution-like behavior. Okay. So what is this transition? So in fact, this is related to the fact that space-like and time-like configuration have different divergence behavior as we take epsilon going to 0. So we can see that by calculating this quantity. When this quantity becomes negative, it means that you have a mu is basically time-like configuration, and when it is positive, it means they are space-like. And yeah, precisely below this critical value of gamma, we have negative value for this quantity, which means that basically the configuration we generate in this region is time-like, whereas those generated here in this region is space-like. So the divergence occurs here, and they are caused by the time-like configurations. And let me skip this. And so the interpretation of the transition is the following. So we have this Pauli matrix, a solution at the saddle point, and we have these symbols, but they are, we can make a Lorentz transformation, and then there are infinitely many equivalent symbols to this original one. And another point here is that along the symbol, actually, this part is space-like, but if you go sufficiently far away from the saddle point, you obtain time-like configuration. This kind of structure explains what we have observed numerically and also by 1 over the expansion. Namely, if this is the case, epsilon, if you would take the epsilon going to 0 limit, then basically time-like configuration dominates, because time-like configuration is the one that has divergence due to the non-compactness of the Lorentz symmetry, whereas the space-like configuration does not have that divergence. Therefore, when you take the epsilon 0 limit first, you basically emphasize this part, blue part, namely the time-like configurations. But if you take large gamma first, then you're focusing near the Pauli solution, and therefore those time-like configurations will be killed. That's the transition. So let me summarize. So Lorentzian IKKT model is not well defined as it is, unlike the Euclidean version studied earlier. And a naive regularization makes it equivalent to the Euclidean model. And therefore, we have proposed a new regularization using a Lorentz invariant mass term, which makes it inequivalent to the Euclidean model. And in the simplest case of n equals 2 bosonic model, we have shown that the partition function for the Pauli symbol diverges due to the non-compact Lorentz transformations of time-like configurations. And as a result, the symbol, Pauli symbol dominates for any positive gamma. This is very surprising, I think. So, well, the trivial saddle point, trivial saddle point never appears in gamma. And the SOD symmetric model can be defined by relation to zero by pi length. But that model does not have these properties. So therefore, these properties are actually genuine Lorentzian nature. Here is the future prospect.
Supersymmetric case, we cannot study by one of these functions because that approach does not respect symmetry. But numerical solution is doable. We are already other end, this method is very costly and it grows grows like n to the 6, but we still do n up to 10 or so. So that's what we are trying to do. And finally, if you want to go to the other end with soothing, maybe this method is not powerful enough, and you can then use the computational method that is going to be discussed by the next speaker. And as you see, the bosonic model simulation suggests 1 plus 1 increase, and Hoppian is already explained. The classic cooperation is not more than 2 extended directions, so we hope that 3 plus 1 dimensional space will finally emerge by doing this.